Hello there, and welcome to Nightfall Science. Tonight, we slowly untangle the physics ideas that often seem confusing. Let your shoulders soften and your eyes grow heavy. The laws of nature will keep quietly working while you rest. Let's begin. Motion only makes sense when it is compared with something else. At first, motion seems simple. An object either moves or it does not. But physics gives this familiar idea a quiet complication. There is no single universal state called motion. There is only motion relative to something else. A person sitting inside a smoothly moving train may appear completely still to another passenger. Their position inside the carriage barely changes. Their hands, shoes, and seat all remain in almost the same places. But someone standing beside the railway sees that same passenger moving rapidly across the landscape. Both descriptions are correct. The difference comes from the frame of reference. A frame of reference is simply the viewpoint used to measure position and motion. The passenger uses the train as a reference. The person outside uses the ground. This becomes even more interesting when Earth itself is considered. A person sitting quietly in a chair seems stationary relative to the room, yet the room moves with Earth as the planet rotates. Earth also travels around the sun. The sun moves through the Milky Way, and the Milky Way itself moves relative to nearby galaxies. Stillness depends on what is being compared. Galileo explored this idea centuries ago. He imagined observers inside smoothly moving ships. If the ship travels at a steady speed, ordinary experiments inside behave normally. A dropped object falls downward. A small insect flies around the cabin. Water drips into a container. Nothing inside reveals some mysterious absolute motion. This principle later became deeply important in Einstein's work. Physics therefore describes motion using relationships. A car may travel at 80 kilometers per hour relative to the road. Another car beside it may travel at nearly the same speed. From inside one vehicle, the other can appear to drift slowly. Two fast-moving objects can seem almost still beside each other. Motion becomes less like a permanent property and more like a comparison. Across Earth, planets, stars, and galaxies, everything moves relative to something else. And beneath all that motion, nature quietly keeps track of the relationships. An object does not need a force to keep moving. This idea feels strange because everyday experience seems to suggest the opposite. A rolling ball eventually stops. A bicycle slows when nobody pedals. A book pushed across a table comes to rest. It can therefore seem natural to imagine that motion itself requires a continuous force. Newton's first law reveals something more subtle. An object naturally keeps its current state of motion unless a net external force changes it. If the object is at rest, it remains at rest. If it moves in a straight line at constant speed, it continues doing so. This property is called inertia. The reason everyday objects usually slow down is not because motion runs out. They slow because other forces act upon them. A rolling ball experiences friction against the ground. Air resistance pushes against it. Tiny deformations in the ball and surface transform some organized motion into thermal energy. Remove those effects, and the ball would continue much longer. Space provides a beautiful example. A spacecraft traveling far from planets can coast for enormous distances after its engines shut down. The engines are needed mainly to change its velocity, not to maintain a constant velocity. This is one reason spacecraft do not need to burn fuel during every moment of a long journey. Inertia also explains why mass matters. A heavy object generally resists changes in motion more strongly than a light one. A full shopping cart is harder to accelerate than an empty cart. It is also harder to stop once it is moving. The mass measures this resistance to acceleration. This does not mean heavy objects somehow contain more motion simply by existing. It means changing their velocity requires a greater net force. Inertia quietly appears everywhere. A cup remains on a desk until something moves it. A moon continues around its planet because gravity continually bends its motion. A distant spacecraft keeps drifting through the dark after its engine becomes silent. Objects do not need constant encouragement to move. Left undisturbed, motion simply continues. Acceleration does not only mean speeding up. In everyday speech, acceleration usually means becoming faster. Physics uses the word more broadly. Acceleration means any change in velocity, and velocity contains two pieces of information. It contains speed. It also contains direction. Because direction matters, An object can accelerate even when its speed remains perfectly constant. A car traveling around a circular track provides a simple example. Its speedometer might stay at 50 kilometers per hour throughout the turn, yet the car continuously changes direction. Its velocity therefore changes. That means the car accelerates. The acceleration points inward toward the center of the circular path. This inward acceleration is often called centripetal acceleration. The same idea appears on much larger scales. The moon moves around Earth without simply flying away in a straight line. Its direction changes continuously because Earth's gravity accelerates it inward. Earth does something similar around the sun. Neither orbit requires the object to constantly become faster. The velocity changes because the direction changes. Acceleration can also mean slowing down. If a moving bicycle loses speed, its velocity changes. Physics therefore describes it as accelerating in a direction opposite its motion. This can sound unusual at first. The word acceleration feels as if it should always point toward greater speed, but mathematically, it simply describes how quickly velocity changes with time. A falling object near Earth's surface provides another familiar case. Ignoring air resistance, gravity gives falling objects an acceleration of roughly 9.8 meters per second squared near the surface. That unusual unit contains an important meaning. For every second of free fall, the object's downward velocity changes by about 9.8 meters per second. Acceleration is therefore not a speed. It describes how speed or direction evolves. A slow-moving object can have enormous acceleration if its velocity changes rapidly. A fast-moving object can have almost no acceleration if it moves steadily in a straight line. In physics, motion has layers. Position changes into velocity. Velocity changes into acceleration. And from these simple changes, the graceful paths of falling stones, turning cars, moons, planets, and stars begin to emerge. Force does not create motion. It changes motion. Newton's second law is often remembered through three compact symbols: F equals ma. Force equals mass multiplied by acceleration. The equation is small enough to fit on a corner of a page, yet it describes an enormous amount of everyday motion. Its meaning becomes clearer when motion and acceleration are separated. A force is not required simply because something is moving. A net force is required when that motion changes. Imagine a puck sliding across nearly frictionless ice. Once moving, it can glide for a long distance with almost constant velocity. If someone pushes sideways, its path bends. If someone pushes forward, it speeds up. If a force acts backward, it slows down. The force produces acceleration. Mass determines how strongly the object responds. The same force applied to a small object creates more acceleration than it creates in a massive object. A gentle push might send an empty chair rolling across a smooth floor. The same push barely changes the motion of a small car. The car contains far more mass. The equation also refers to net force. Several forces can act on the same object at once. A book resting on a table provides a quiet example. Gravity pulls the book downward. The table pushes upward on the book through what physicists call the normal force. If those forces balance, the net force is zero. The book does not accelerate. This sometimes creates confusion because zero net force does not mean that no forces exist. It means the forces balance. The same can happen while an object moves. A car traveling at constant velocity along a level road may have its engine providing forward force while resistance acts backward. If the forces balance, acceleration becomes zero and the velocity remains constant. Newton's second law is therefore a rule about change. Large net force produces larger acceleration. Large mass resists that acceleration. Balanced forces produce no acceleration at all. From a resting book to an orbiting satellite, the same quiet relationship remains. Force tells motion how to change. Every push comes with a partner. Newton's third law is famous for a simple statement: for every action, there is an equal and opposite reaction. The phrase can sound mysterious because it seems to suggest that forces should always cancel, but the two forces act on different objects. That detail makes everything clearer. When a person stands on the ground, gravity pulls the person toward Earth. At the same time, the person gravitationally pulls Earth toward them. The forces are equal in magnitude and opposite in direction. Earth barely moves because its mass is enormous compared with a human body. Walking provides another example. A foot pushes backward against the ground. The ground pushes forward against the foot. That forward force helps move the body. Swimming follows a similar pattern. A swimmer pushes water backward. The water pushes the swimmer forward. Bird flight also depends on interacting forces between wings and air. Rockets provide one of the clearest demonstrations. A rocket engine sends hot exhaust gases rapidly backward. Those gases are pushed by the rocket. At the same time, the gases exert an equal and opposite force on the rocket. The rocket moves forward. Nothing nearby needs to be pushed against. That is why rockets work in the vacuum of space. The interaction occurs between the spacecraft and its exhaust. Even a simple object resting on a table reveals paired forces, although they must be identified carefully. The table pushes upward on the book. The book pushes downward on the table. Those two forces form a third law pair. The gravitational pull of Earth on the book has a different partner, the gravitational pull of the book on Earth. Every interaction involves this quiet symmetry. One object pulls another, and the other pulls back. One surface pushes another, and the other pushes back. The partners may respond very differently because their masses differ, yet the forces themselves arrive together. Nature never sends a force alone. Momentum allows motion to be passed from one object to another. Momentum combines two familiar properties, mass and velocity. In classical mechanics, momentum equals mass multiplied by velocity. A light object moving slowly has little momentum. A massive object moving quickly can have much more. But the deeper importance of momentum comes from its conservation. In an isolated system, the total momentum remains constant. Momentum can move between objects. It can change direction. It can be divided among many pieces. But the total remains balanced when no external net force interferes. Billiard balls provide a familiar picture. One moving ball strikes another resting ball. After the collision, the first may slow while the second begins moving. Some of the original momentum transfers from one ball to the other. The details depend on the collision. Energy may transform into sound, heat, rotation, or small deformations. Yet total momentum remains conserved. The same principle explains recoil. When a person standing on a low-friction surface throws a heavy object forward, the person's body moves gently backward. Before the throw, the total momentum may be zero. Afterward, the forward momentum of the thrown object is balanced by backward momentum elsewhere in the system. Rockets again offer a much larger example. Exhaust carries momentum backward. The spacecraft gains momentum forward. Momentum conservation also works in events far beyond everyday life. Particles collide inside accelerators. Stars eject matter. Exploding objects send fragments in many directions. Physicists can examine the motion afterward and reconstruct parts of what occurred before. Momentum acts almost like an accounting system for motion. Individual objects may gain or lose it. The system keeps the total balanced. This principle is especially useful because it survives situations where the individual forces become complicated. A collision can last only a tiny fraction of a second. The forces during that instant may vary rapidly, yet momentum before and after remains a powerful guide. Motion can be shared. Motion can be redirected. Motion can spread through many objects, and through every quiet exchange, momentum keeps the record. Work in physics is not simply effort. In everyday language, work can mean almost any difficult activity. Carrying boxes feels like work. Holding a heavy bag feels like work. Standing still for a long time can feel exhausting. Physics gives the word a much narrower meaning. Mechanical work happens when a force causes displacement. In its simplest form, work equals force multiplied by the distance moved in the direction of that force. This creates several results that can initially feel unusual. Suppose a person holds a heavy box completely still. The muscles are active. Chemical energy is being used. The person may become tired, but from the viewpoint of basic mechanics, no work is being done on the box because the box does not move. There is force, but there is no displacement. Now imagine the same box being lifted upward. The person applies an upward force while the box moves upward. Mechanical work is now being done on the box. The concept also depends on direction. If a force acts perpendicular to an object's motion, that force may do no mechanical work. An object moving in a circle provides an important example. For uniform circular motion, the centripetal force points toward the center, while the instantaneous motion points along the circle. Those directions are perpendicular. The inward force changes the direction of motion without necessarily changing the object's speed. In that ideal case, the centripetal force does no work. The unit of work is the joule. 1 joule is the work done when a force of 1 Newton moves something 1 meter in the force's direction. The same unit is also used for energy. That connection is not an accident. Work is one of the main ways energy moves into or out of a system. Pushing a cart can increase its kinetic energy. Lifting an object can increase its gravitational potential energy. Compressing a spring can store elastic potential energy. Work, therefore, connects force, distance, and energy. It does not measure how tiring an activity feels. It measures how force transfers energy through motion. And with that simple distinction, a familiar word becomes part of the quiet bookkeeping of nature. Kinetic energy belongs to motion. Anything moving possesses kinetic energy. A drifting leaf has some. A rolling bicycle has more. A speeding train carries an enormous amount. In classical mechanics, kinetic energy is 1/2 of mass multiplied by velocity squared. That final square changes everything. Doubling the mass doubles the kinetic energy if speed stays constant. Doubling the speed produces 4 times the kinetic energy. Tripling the speed produces 9 times as much. Speed, therefore, has a particularly strong influence. This is why 2 vehicles with similar masses can carry very different amounts of kinetic energy when their speeds differ. The equation also explains why stopping distance becomes increasingly important at greater speeds. A faster object contains much more kinetic energy that must be transferred elsewhere before it can stop. Brakes transform organized motion into thermal energy. Tires and road surfaces warm slightly. Air is disturbed. Tiny vibrations spread through materials. The energy does not simply vanish. Kinetic energy can also pass between objects. A moving billiard ball can strike another and set it in motion. A flowing river can turn a turbine. Moving air can push the blades of a wind turbine. Microscopic motion matters as well. Inside warm materials, atoms and molecules move in complicated ways. Temperature is related to the average microscopic kinetic energy of particles, although the full description depends on the system. On very small scales, quantum mechanics changes the classical picture. At speeds approaching the speed of light, relativity changes it again. But for ordinary objects moving at ordinary speeds, the familiar expression works beautifully. A thrown stone, a running animal, a rotating wheel, and a planet moving around the sun all possess kinetic energy. The forms of motion differ. The same underlying idea remains. Whenever matter moves, energy travels with that motion. Potential energy belongs to arrangements. Potential energy can seem less intuitive than kinetic energy. Kinetic energy is easy to picture because something visibly moves. Potential energy may exist while everything appears completely still. Its meaning comes from configuration. A system can store energy because of the positions or arrangements of its parts. A book resting high on a shelf provides a simple example. Earth and the book gravitationally interact. If the book falls, gravitational potential energy decreases while kinetic energy increases. The stored possibility of motion comes from the arrangement of the book and Earth. Near Earth's surface, gravitational potential energy can often be approximated as mass multiplied by gravitational acceleration multiplied by height. The expression works well when height changes are small compared with Earth's radius. Farther away, gravity requires a more complete description. Springs provide another form. A compressed or stretched spring stores elastic potential energy. Release the spring, and that stored energy can become motion. Chemical systems also store energy through electromagnetic interactions among atoms and molecules. The phrase potential energy does not mean that energy is somehow hidden inside an object as a separate substance. Often it belongs to the relationship between parts of a system. A raised object and Earth form a gravitational arrangement. 2 electric charges have potential energy because of their positions relative to one another. A stretched spring has energy because of the arrangement of its material. This is why the 0 point of potential energy can often be chosen conveniently. What matters physically is usually the change in potential energy. A mountain climber can define sea level as 0 height. An engineer working with a spring can choose the relaxed position as a convenient reference. The numerical 0 may move. The physical differences remain. Potential energy is therefore an elegant way of describing possibilities created by arrangement. A system may look perfectly quiet, yet its configuration can contain the ability to produce motion later. Sometimes the stillest looking systems are simply waiting for energy to change form. energy changes form without disappearing. The conservation of energy is one of physics' most powerful ideas. Energy can move, it can spread, it can change form, but in an isolated system, the total amount remains conserved. A swinging pendulum makes this easy to imagine. At the highest point of its swing, the pendulum moves slowly. Its gravitational potential energy is relatively high. As it falls, that potential energy decreases. Its speed increases. Kinetic energy grows. Near the bottom, the pendulum moves fastest. Then it rises again. Kinetic energy changes back into gravitational potential energy. In an ideal pendulum, with no friction, this exchange would continue indefinitely. A real pendulum gradually slows. At first, this can seem like lost energy. But the energy has not disappeared. Air resistance creates motion in the surrounding air. Friction warms the pivot. Sound waves carry some energy away. Eventually, the pendulum's organized mechanical energy becomes dispersed among many microscopic forms. The same pattern appears when a ball bounces. Each bounce becomes lower. Mechanical energy decreases. But energy moves into sound, internal vibrations, deformation, and thermal motion. Conservation becomes especially useful because energy has many forms. There is kinetic energy, gravitational potential energy, elastic energy, chemical energy, electromagnetic energy, nuclear energy, thermal energy. Mass itself is connected with energy through relativity. Different areas of physics use different descriptions, yet the accounting remains remarkably consistent. Energy may become difficult to recover for a useful task. It may spread into countless microscopic motions. That does not mean it has vanished. The conservation law is one reason physicists can analyze systems without following every detail. If the energy at one moment is known, the possible outcomes become constrained. Nature may rearrange energy in astonishingly complicated ways, yet the total remains balanced. Across falling objects, glowing stars, gravity is not simply a force that pulls things downward. Near Earth's surface, gravity feels simple. Objects fall toward the ground. Rain moves downward. A dropped cup accelerates toward the floor. This makes it easy to imagine gravity as a force that always points down. But downward is only a local description. Gravity pulls masses toward one another. Near Earth, the planet is so massive that its influence dominates everyday motion. The direction called down, therefore, points roughly toward Earth's center. On the opposite side of the planet, down points in the opposite direction through space. People there do not feel upside down. Their local vertical simply points toward the center of Earth. Newton described gravity with a remarkably successful mathematical law. Every mass attracts every other mass. The strength of the attraction increases with the masses involved. It decreases rapidly as the distance between them grows. More precisely, the gravitational force follows an inverse square relationship. Double the distance between two objects, and the force becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. Gravity is weak compared with some other fundamental interactions, yet it dominates the large-scale structure of the universe. The reason is simple. Gravity has an enormous range, and ordinary matter contains positive mass, so gravitational effects usually add together instead of canceling. A tiny object has a tiny gravitational pull. A planet combines the gravity of an unimaginable number of particles. A star contains far more mass still. Entire galaxies contain enough mass for gravity to guide billions of stars. Newton's description works beautifully for most familiar situations. Einstein later provided a deeper picture through general relativity. In that theory, gravity is connected with the geometry of space-time. Mass and energy influence that geometry. Objects then follow the natural paths available within the curved space-time. For most everyday calculations, Newton's picture remains extremely accurate. For very strong gravity or very precise measurements, Einstein's description becomes essential. A falling apple, an orbiting moon, and a galaxy full of stars appear very different, yet all participate in the same quiet gravitational structure. Gravity does not simply point downward, it reaches outward through space, shaping paths on scales from falling dust to clusters of galaxies. Mass and weight are not the same thing. The words mass and weight are often used as if they mean the same thing. In physics, they describe different properties. Mass measures an object's inertia. It describes how strongly an object resists changes in motion. Mass also contributes to gravitational interactions. For an ordinary object, its mass does not suddenly change when it travels from Earth to the Moon. Weight is different. Weight depends on gravity. In simple situations, weight is the gravitational force acting on an object. A person with a mass of 60 kilograms has the same mass on Earth and on the Moon. But the person's weight is much smaller on the Moon because the Moon's gravitational field is weaker. This distinction explains the familiar images of astronauts moving with long, gentle steps across the lunar surface. Their bodies still contain the same amount of mass. Their inertia remains. Accelerating a heavy piece of equipment sideways is still influenced by that mass, but everything weighs less. Earth's gravitational acceleration near the surface is about 9.8 meters per second squared. On the Moon, it is about 1.6 meters per second squared. A person's lunar weight is therefore roughly 1/6 of their Earth weight. Mass is usually measured in kilograms. Weight, because it is a force, is properly measured in newtons. Everyday bathroom scales blur this distinction. They usually display kilograms even though they detect a force. They are calibrated for Earth's gravity and translate the measured force into a mass value. Move the same scale to another world without recalibration, and the reading becomes misleading. Weight can even appear to vanish temporarily. Astronauts in orbit often experience what is called weightlessness. Their mass has not disappeared. Earth's gravity has not disappeared either. Instead, the spacecraft and everything inside are falling together. This creates the sensation of floating. Mass stays with the object. Weight depends on the gravitational situation around it. One remains a property of matter. The other describes an interaction. A quiet difference in words reveals two different ways physics understands matter. Heavy and light objects fall together in a vacuum. This idea once seemed deeply unnatural. A stone feels heavier than a feather. Drop both in ordinary air, and the stone reaches the ground first. It seems reasonable to assume that stronger gravity must make heavier objects fall faster. But the full story contains a balance. A more massive object does experience a larger gravitational force. At the same time, it also has more inertia. It resists acceleration more strongly. These two effects increase together. Near Earth's surface, when air resistance is ignored, the result is the same gravitational acceleration for objects of different masses. A heavy ball and a light ball released together in a vacuum fall side by side. Their masses differ. Their weights differ. Their acceleration is essentially the same. Galileo is strongly associated with this insight. Centuries later, astronauts demonstrated it in a striking way on the Moon. During the Apollo 15 mission, astronaut David Scott dropped a hammer and a feather together. With almost no atmosphere to slow the feather, both reached the lunar surface at nearly the same time. Earth produces the same principle. The atmosphere simply hides it. Air resistance affects objects differently depending on shape, area, speed, and other factors. A broad feather experiences a large drag force compared with its weight. A compact stone experiences proportionally less. Remove the air, and the difference largely disappears. This is closely related to the equivalence principle that later became central to Einstein's thinking. Gravitational acceleration does not depend on the composition of the falling object in the simple way intuition might suggest. Modern experiments test this principle with extraordinary precision. The result has deep consequences. Gravity treats freely falling objects with a remarkable universality. A metal sphere, a glass sphere, and a carefully isolated collection of atoms all follow the same basic gravitational rule. Different objects can have very different masses, yet in free fall, gravity gives them the same gentle acceleration when other forces are removed. Terminal velocity appears when falling stops becoming faster. A falling object does not always continue gaining speed indefinitely. Near Earth's surface, gravity pulls downward. At the same time, air pushes against the motion. This resistive effect is called drag. At first, when an object begins to fall, its speed is low. The drag force is relatively small. Gravity therefore produces a strong net downward force. The object accelerates. As its speed increases, air resistance grows. The faster the object moves through the air, the stronger the drag generally becomes. Eventually, a special balance may occur. The downward gravitational force becomes equal in magnitude to the upward drag force. The net force becomes zero. Acceleration becomes zero. The object continues falling, but its speed stops increasing. This steady falling speed is called terminal velocity. Terminal velocity is not the same for every object. Mass matters, shape matters, cross-sectional area matters, air density matters. The drag properties of the object matter as well. A compact object with a large mass can have a high terminal velocity. A light object with a broad surface can have a much lower one. A parachute works by dramatically increasing drag. Opening the canopy creates a large area that interacts with the air. The falling system slows until a new, much lower terminal velocity is reached. Tiny particles can have remarkably low terminal velocities. Dust may remain suspended in air for long periods. Cloud droplets can fall very slowly because their small size changes the balance between gravity and drag. Rain becomes more complicated because droplets grow, deform, collide, and move through turbulent air. Terminal velocity is therefore a simple concept with many different expressions. The same basic balance also appears outside Earth's atmosphere. Objects moving through water experience drag. Spacecraft entering an atmosphere experience enormous aerodynamic forces. Seeds drifting from plants use shapes that increase air resistance and extend their time aloft. A falling object can therefore pass through two different stages. First, gravity changes its speed. Then resistance grows until the forces balance. After that, the object continues downward almost peacefully, no longer becoming faster. The center of mass lets many particles behave like one point. Most real objects are not single points. A book contains countless atoms. A person has arms, legs, bones, muscles, and organs. A planet is an enormous three-dimensional collection of matter. Yet physicists can often describe the motion of an entire object using one imagined location. This location is called the center of mass. The center of mass represents the average position of mass within a system. For a perfectly uniform sphere, it lies at the geometric center. For an irregular object, it may lie somewhere else. It does not even have to lie inside the material itself. A ring provides a simple example. Its center of mass lies in the empty space at the middle. A boomerang or curved object can also have a center of mass located outside its physical surface. The idea becomes particularly useful when objects move. A thrown wrench may tumble through the air in a complicated way. Different parts rotate along different paths, yet its center of mass follows a much simpler trajectory, ignoring air resistance. That point moves like an ordinary projectile under gravity. The object spins around while the center of mass traces a smooth path. The same reasoning applies to groups of objects. Two stars orbiting each other revolve around their shared center of mass. If one star is much more massive, the center lies close to the heavier star. If their masses are similar, the center lies somewhere between them. Earth and the Moon also orbit a common center of mass called their barycenter. Because Earth is much heavier than the Moon, this point lies inside Earth, though not exactly at Earth's center. The Sun itself makes small motions around the solar system's barycenter as planets move around it. The center of mass reduces complexity. Millions of moving pieces can often be treated as if their total mass were concentrated at one mathematical point for certain calculations. The internal motion does not disappear. It simply becomes separated from the motion of the whole system. A tumbling object may look complicated. Its parts twist and rotate. Through that complexity, the center of mass follows a quieter path. Torque is the turning version of force. A force does not always make an object move straight ahead. Sometimes it makes an object rotate. The quantity that describes this turning effect is called torque. Torque depends on the force. It also depends on where the force is applied relative to the axis of rotation. A door provides an everyday example. Push near the hinges, and the door is difficult to rotate. Push with the same force near the handle, and the door turns much more easily. The force has not changed. The distance from the hinge has. That distance gives the force a larger lever arm. The resulting torque becomes greater. This principle appears in tools. A long wrench makes it easier to turn a stubborn bolt. The longer handle allows the same force to produce more torque around the bolt. A seesaw also depends on torque. A light person sitting far from the pivot can balance a heavier person sitting closer. The turning effects on opposite sides can become equal. When clockwise and counterclockwise torques balance, rotational acceleration can be zero. Torque is related to angular acceleration in much the same way ordinary force is related to linear acceleration. But rotation introduces another property called moment of inertia. Moment of inertia describes how strongly an object resists changes in its rotational motion. Mass matters. The distribution of that mass matters too. Mass located far from the rotation axis contributes strongly to the moment of inertia. This explains a familiar motion in figure skating. When a spinning skater pulls their arms inward, mass moves closer to the rotation axis. The moment of inertia decreases. With angular momentum approximately conserved, the rotation becomes faster. Extending the arms slows the spin again. Torque appears in machines, bicycles, engines, planets, and human joints. Muscles create forces around joints. Motors create torque around shafts. Gravity can create torque on unevenly supported objects. Rotation is not separate from the rest of mechanics. It is another expression of the same basic principles. A push can change where something goes. Applied at the right distance and direction, the same push can quietly change how something turns. Angular momentum keeps rotation remarkably steady. Linear momentum describes motion along a path. Rotating systems have a related quantity called angular momentum. Angular momentum depends on how much mass is moving, how fast it rotates, and how that mass is distributed around the rotation axis. When no external torque acts, total angular momentum remains conserved. This principle explains many motions that initially seem surprising. A spinning figure skater provides the classic example. With arms extended, much of the skater's mass lies farther from the rotation axis. The moment of inertia is relatively large. When the arms move inward, the moment of inertia decreases. Angular momentum must remain nearly constant. The rotation therefore becomes faster. Nothing mysterious adds extra rotation. The same angular momentum is simply distributed differently. A person sitting on a freely rotating chair can experience the same effect. Holding weights with arms extended produces slower rotation. Pulling the weights inward increases the rotation rate. Move them outward again, and the rotation slows. Angular momentum also appears far beyond human scale motion. A collapsing cloud of gas can begin with only a gentle rotation. As gravity pulls the material inward, the cloud becomes smaller. Its rotation may become faster as angular momentum is conserved. This process contributes to the formation of stars and planetary systems. Planets also carry angular momentum as they orbit the Sun. The solar system's total angular momentum is shared among the Sun, planets, moons, asteroids, and smaller bodies. Collisions and gravitational interactions can transfer angular momentum between objects, but within an isolated system, the total remains conserved. Angular momentum also helps explain why spinning objects often resist changes to their orientation. A rapidly spinning bicycle wheel can behave differently from a stationary one. Gyroscopes use this stability. When forces try to change the direction of the rotation axis, the response can appear sideways. This behavior is called precession. Earth itself behaves somewhat like an enormous rotating gyroscope. Its axis slowly precesses over thousands of years, because gravitational torques from the Sun and Moon act on Earth's equatorial bulge. Rotation therefore carries a kind of persistence. A spinning object contains not only motion, but organized rotational motion. And unless an outside torque changes the balance, that rotation quietly keeps its account. Centrifugal force depends on the frame being used. Circular motion introduces one of physics's most confusing pairs of words: centripetal force and centrifugal force. Centripetal means center-seeking. Any object moving in a circle needs an inward acceleration. That inward acceleration requires a net force pointing toward the center. The source of the force depends on the situation. For a car turning on a road, friction can provide it. For a planet orbiting a star, gravity provides it. For a ball attached to a string, tension provides it. Centripetal force is therefore not a new fundamental force. It is simply the name given to the net inward force producing circular motion. Centrifugal force is more subtle. Imagine sitting inside a car as it turns left. The body seems to be pushed toward the right side of the car. From the viewpoint of someone standing beside the road, the explanation is straightforward. The body naturally tends to continue along a straighter path because of inertia. The car turns left beneath it. The seat and door then provide forces that redirect the body. But inside the turning car, it can feel as if an outward force exists. In a rotating frame of reference, physicists can introduce an apparent centrifugal force to describe this effect. It points outward. This does not make it imaginary in the sense of being useless. It simply means the force appears because the chosen frame itself is accelerating. Rotating reference frames can be very useful. Weather systems on Earth are often described using another apparent effect called the Coriolis force. Because Earth rotates, moving air and water appear to curve relative to the surface. The underlying physics can be described from a non-rotating frame without introducing these apparent forces. But from Earth's rotating surface, using them makes calculations much easier. Physics often allows several descriptions of the same motion. The important step is knowing which frame is being used. An inward force creates circular motion. An outward effect may appear in the rotating frame. Both descriptions can be useful when their viewpoints remain clear. Oscillations appear whenever systems repeatedly return toward equilibrium. A pendulum swings from side to side. A guitar string moves back and forth. A ruler hanging over the edge of a table vibrates when disturbed. These motions belong to a broad family called oscillations. An oscillating system repeatedly moves around an equilibrium position. Equilibrium is the configuration where competing influences balance, move the system away from that position, and a restoring force tends to bring it back. A simple spring offers a clear example. Stretch the spring, it pulls inward. Compress it, it pushes outward. For an ideal spring, the restoring force is approximately proportional to the displacement. This relationship is known as Hooke's law. Because the restoring force always points back toward equilibrium, the mass attached to the spring can move repeatedly from side to side. In an ideal situation, this produces simple harmonic motion. Simple harmonic motion has a smooth mathematical form closely related to sine and cosine waves. Position changes gently through time. Velocity becomes greatest as the object passes through equilibrium. At the outermost points, the velocity momentarily becomes zero. Energy moves continuously between forms. In a spring system, elastic potential energy is greatest near maximum compression or extension. Kinetic energy becomes greatest near the central position. A pendulum follows a similar exchange when its swings are small. Near the ends of its path, gravitational potential energy is high and speed is low. Near the bottom, speed is greatest. Real oscillations rarely continue forever. Air resistance and friction gradually remove mechanical energy from the organized motion. This effect is called damping. The amplitude becomes smaller. The motion settles. Oscillations appear throughout nature. Buildings sway. Atoms vibrate inside solids. Electric circuits can oscillate. Stars can pulsate. Even molecules possess characteristic vibrational motions. A simple back-and-forth movement becomes a pattern found across enormous ranges of scale. Again and again, nature moves away from balance, returns, passes through, and gently comes back. A wave can travel even when matter does not travel with it. Watching an ocean wave can create the impression that water moves forward with the wave. But the individual water particles usually follow much smaller paths. The wave travels. Most of the water remains in roughly the same region. This difference is central to understanding waves. A wave is a traveling disturbance that transfers energy and momentum. The material carrying the wave does not necessarily travel the full distance with it. Imagine shaking one end of a long rope. A pulse moves along the rope. Each small section of rope moves only a limited distance, often mostly up and down, yet the disturbance travels from one end toward the other. The same principle appears in sound. Sound traveling through air does not require air molecules to fly from the speaker all the way to the listener. Instead, molecules oscillate around their local positions. Regions of slightly higher and lower pressure travel through the air. Energy moves through the medium. Waves can be classified in different ways. In a transverse wave, the disturbance is perpendicular to the direction the wave travels. A stretched string provides an approximate example. The wave travels horizontally, while the string moves vertically. In a longitudinal wave, the disturbance occurs mostly along the direction of travel. Sound waves in air are a familiar example. Compressions and rarefactions move forward while molecules oscillate back and forth. Some waves require a material medium. Sound cannot travel through a perfect vacuum because there are no particles to carry the pressure disturbance. Electromagnetic waves are different. Light can travel through empty space. Its changing electric and magnetic fields propagate even where matter is absent. This allows sunlight to cross roughly 150 million kilometers of space before reaching Earth. A wave is therefore not necessarily a moving collection of material. It is a pattern moving through a system. Particles may only wiggle gently around their positions. Yet the pattern can travel across oceans, through air, along strings, or between stars. Wavelength and frequency describe different parts of the same rhythm. Every repeating wave has a spatial pattern and a timing pattern. Wavelength describes the spatial part. Frequency describes the timing. Wavelength is the distance between equivalent points on successive cycles. For a simple wave, it might be measured from one crest to the next. Frequency tells how many complete cycles pass a point each second. Its unit is the hertz. 1 hertz means 1 cycle per second. A wave with a frequency of 100 hertz completes 100 cycles every second. Wavelength, frequency, and wave speed are connected. The wave speed equals frequency multiplied by wavelength. If the speed stays constant, increasing the frequency makes the wavelength shorter. Decreasing the frequency makes the wavelength longer. Sound provides an intuitive example. In air under the same conditions, higher frequency sounds generally have shorter wavelengths. Lower frequency sounds have longer wavelengths. Human hearing detects only part of the enormous range of possible sound frequencies. Young, healthy listeners commonly hear frequencies from roughly 20 Hz to around 20,000 Hz, though sensitivity varies, and the upper limit often decreases with age. Below the usual hearing range lies infrasound. Above it lies ultrasound. Other animals detect different ranges. Electromagnetic waves also form a continuous spectrum. Radio waves can have wavelengths longer than buildings. Microwaves are shorter. Infrared becomes shorter still. Visible light occupies only a narrow region. Beyond it lie ultraviolet radiation, X-rays, and gamma rays. All of these are electromagnetic waves. They differ mainly in frequency and wavelength. In vacuum, they all travel at the same fundamental speed, the speed of light. A radio signal and a beam of visible light therefore belong to the same broad physical family. One may stretch across meters, another may have wavelengths measured in hundreds of nanometers. Different scales reveal different behaviors, but beneath them sits the same quiet relationship between distance, rhythm, and speed. Resonance allows small, repeated pushes to create large motion. A playground swing offers one of the easiest ways to understand resonance. A swing naturally prefers to move back and forth at a certain characteristic frequency. Give a small push at the right moment during each cycle, and the motion gradually becomes larger. Each push adds energy in step with the existing oscillation. The individual pushes can be gentle. Their timing is what matters. This phenomenon is called resonance. Many physical systems possess natural frequencies. A stretched string has them. A column of air inside a musical instrument has them. Buildings have them. Bridges have them. Atoms and molecules have characteristic frequencies as well. When an external influence repeatedly drives a system near one of its natural frequencies, energy transfer can become especially efficient. Musical instruments use resonance deliberately. A guitar string alone produces only a modest sound. The body of the guitar interacts with the vibrating string and the surrounding air. Resonant behavior helps produce a stronger, richer sound. Wind instruments use resonances in columns of air. Changing the effective length of the air column changes which frequencies are strongly supported. Resonance also explains why one tuning fork can influence another tuning fork with the same natural frequency. Sound waves from the first fork provide repeated forces. The second responds most effectively when those forces match its preferred rhythm. Real systems include damping. Friction and resistance remove energy. Because of this, resonance does not normally lead to unlimited growth. Instead, the amplitude settles where energy supplied by the driving force balances energy being dissipated. Engineers pay careful attention to resonance. Machines can produce repeated vibrations. Structures have natural modes. If the frequencies align too closely, motion may become much larger than expected. Designs can therefore shift natural frequencies or add damping. Resonance is not unusual or exotic. It is one of the most common features of oscillating systems. A quiet rhythm meets another rhythm. When their timing agrees, energy passes between them with unusual ease. Waves can pass through one another without permanently changing. When two ordinary objects collide, they usually affect each other's motion. Waves behave differently. Two waves can overlap in the same region at the same time. During that overlap, their effects combine. Then they continue onward. This principle is called superposition. Imagine two small pulses traveling toward each other along a rope. For a brief moment, they meet. The rope's displacement becomes the sum of both pulses. Afterward, the pulses separate and continue along their original paths. The waves do not have to bounce away like solid objects. Their temporary combination creates interference. When two wave displacements point in the same direction, they reinforce one another. This is called constructive interference. The resulting displacement becomes larger. When they point in opposite directions, they can partially or completely cancel. This is called destructive interference. The word cancellation can sound as if energy disappears. It does not. The energy remains within the full wave system and continues to move through it. Interference appears in sound. Two speakers producing similar tones can create locations where sound is stronger and others where it becomes quieter. Move around the room, and the loudness may change because the waves arrive with different phases. Interference also appears in light. The famous double-slit experiment produces alternating bright and dark regions. Light reaching some locations combines constructively. At other locations, it combines destructively. This pattern helped reveal the wave nature of light. Modern technology uses interference deliberately. Noise-canceling headphones produce sound designed to partially oppose unwanted sound waves near the ear. Optical instruments use carefully controlled interference to measure tiny distances. Astronomical interferomotors combine signals from separated telescopes to reveal extremely fine details. The principle remains simple beneath these sophisticated uses. Waves overlap, their effects add, then they move on. Two patterns can occupy the same place for a moment and quietly pass through one another. Diffraction makes waves spread around obstacles. Waves do not always travel in perfectly straight lines. When they pass through an opening or around an edge, they can spread into regions that might otherwise seem hidden. This behavior is called diffraction. Its strength depends strongly on the relationship between wavelength and size. If an opening is much larger than the wavelength, the wave may pass through with relatively little spreading. If the opening is comparable to the wavelength, diffraction becomes much more noticeable. Water waves offer a gentle visual example. Imagine waves moving toward a barrier containing a narrow gap. After passing through, the waves spread outward in curved fronts. The opening behaves almost like a new source of waves. Sound also diffracts. This is one reason a voice can sometimes be heard around a corner, even when the speaker cannot be seen. Sound wavelengths can be similar to the sizes of doorways, walls, and everyday objects. The waves bend and spread around boundaries. Visible light has much shorter wavelengths. Ordinary objects are usually enormous compared with those wavelengths. As a result, light often appears to travel in nearly straight lines and produces relatively sharp shadows. Yet light also diffracts when it encounters sufficiently small openings or structures. A narrow slit can make a beam spread. Closely spaced structures can create distinctive diffraction patterns. CDs and DVDs produce rainbow-like colors, partly because their tiny surface tracks interact with light through diffraction and interference. X-ray diffraction allows scientists to study the arrangement of atoms inside crystals. The wavelengths of X-rays are comparable to atomic spacings. The resulting patterns contain information about structures too small to see directly. Diffraction therefore connects everyday waves with microscopic measurements. A sound wrapping around a doorway and an X-ray revealing a crystal both follow the same broad principle. Wave behavior depends on scale. When wavelengths become comparable with the structures they encounter, straight paths soften into spreading patterns. Waves seem to explore the space around them rather than following only one narrow route. Standing waves appear when motion forms a pattern that seems still. Most waves travel from one place to another. Standing waves look different. Their overall pattern remains in approximately the same location. Parts of the system move strongly. Other points hardly move at all. A standing wave often forms when waves of the same frequency travel in opposite directions and interfere. A stretched string provides a familiar example. Pluck a guitar string. Waves travel along the string, reflect from the fixed ends, and overlap. At certain frequencies, the overlapping waves create stable patterns. Some points remain nearly motionless. These are called nodes. Between the nodes lie regions of larger motion called antinodes. The simplest standing wave pattern on a string has nodes at both ends and one large antinode in the middle. This is the fundamental mode. Higher modes contain additional nodes and antinodes. Their frequencies are related to the fundamental frequency. These patterns help determine the sound of stringed instruments. A guitar string does not usually vibrate at only one frequency. Its motion can contain the fundamental and several higher harmonics. The mixture contributes to the characteristic tone. Standing waves also form in air columns. Flutes, organ pipes, clarinets, and many other instruments use resonant patterns in the air. The exact frequencies depend on the pipe length and whether its ends behave as open or closed boundaries. Microwave ovens can produce standing electromagnetic wave patterns inside their cavities. Rotating trays help move food through regions of stronger and weaker field intensity, so heating becomes more even. Standing waves also appear in buildings, mechanical structures, and quantum systems. The mathematics changes with the situation, but the pattern remains familiar. Traveling waves overlap. Their motions combine. Certain locations become quiet. Others move repeatedly. A standing wave is therefore not truly motionless. It is a carefully balanced form of motion. Energy shifts through a pattern whose shape remains quietly in place. Pitch and loudness describe different features of sound. A high note and a loud note are not the same thing. Pitch is connected mainly with frequency. Loudness is connected mainly with the strength of the sound reaching the ear. When a sound wave has a higher frequency, it is usually perceived as having a higher pitch. A lower frequency usually produces a lower pitch. A piano demonstrates this clearly. Its longer, heavier strings generally produce lower frequency notes. Shorter, lighter strings can vibrate more rapidly and produce higher notes. Human hearing interprets frequency through the mechanical and neural structures of the ear. Different regions of the inner ear respond most strongly to different frequencies. Loudness comes from a different aspect of the wave. A sound wave consists of changing pressure in a medium. Larger pressure variations generally carry more intensity. The ear usually perceives this as a louder sound. The relationship between physical intensity and perceived loudness is not perfectly simple. Human hearing covers an enormous range of intensities. Because of this, sound levels are often expressed using the logarithmic decibel scale. A modest numerical change in decibels can represent a much larger change in physical intensity. The perception of loudness also depends on frequency. Human ears are more sensitive to some frequencies than others. Two sounds with identical physical intensities can therefore seem to have different loudness. Tone contains still more information. A violin and a flute can play the same musical note at the same apparent loudness, while sounding distinctly different. Their waveforms contain different mixtures of frequencies and evolve differently through time. This quality is often called timbre. Sound therefore carries several layers at once. Frequency contributes to pitch. Amplitude and intensity contribute to loudness. Harmonics and timing contribute to tone quality. A single pressure wave reaching the ear can contain all of these features. From that changing pressure, the brain quietly constructs the rich world of speech, music, footsteps, rainfall, and distant wind. The Doppler effect changes frequency when sources and observers move. A passing siren offers a familiar demonstration. As the vehicle approaches, the pitch sounds higher. After it passes and moves away, the pitch becomes lower. The siren itself does not need to suddenly change the frequency it produces. The change comes from relative motion. This is the Doppler effect. Imagine a sound source moving through still air. Each new wave crest is emitted from a slightly different position. In front of the moving source, the wavefronts become more closely spaced. The wavelength becomes shorter. Behind the source, they become more widely spaced. The wavelength becomes longer. Because the speed of sound through the same air remains approximately fixed, shorter wavelength corresponds to higher frequency, longer wavelength corresponds to lower frequency. An observer in front therefore receives wave crests more frequently. An observer behind receives them less frequently. The effect also occurs when the observer moves. What matters is the relative motion between the source, the observer, and the medium for ordinary sound. Light shows a related Doppler effect. When a source of light moves away, its observed wavelengths can shift toward longer wavelengths. This is called redshift. When it moves closer, wavelengths can shift toward shorter values, producing blue shift. Astronomers use these shifts to measure motion across extraordinary distances. The spectral lines of stars and galaxies contain recognizable patterns. If the whole pattern shifts slightly, the motion along the line of sight can be estimated. The Doppler effect also helps reveal planets around distant stars. An orbiting planet gravitationally tugs on its star. The star makes a small repeating motion. Sensitive measurements can detect the resulting changes in its spectral lines. The same principle appears in radar speed measurements, medical ultrasound, weather observations, and many other technologies. A passing siren and a distant star seem unrelated, yet both reveal motion through changing wave frequency. Movement quietly changes the spacing between arriving waves. Pressure comes from countless tiny collisions. Pressure can feel like a smooth, continuous property. Air presses on a window. Water presses against the wall of a container. A tire becomes firm when filled. At the microscopic level, however, this smooth pressure emerges from enormous numbers of particle interactions. Gas molecules move continuously. They travel in different directions with a range of speeds. When they strike a surface, they change momentum. The surface experiences a force. One molecular collision produces almost nothing noticeable, but countless collisions occur every moment. Their combined effect becomes pressure. Pressure is defined as force divided by area. The same force concentrated over a small area creates greater pressure than when spread over a larger area. This explains why a sharp needle penetrates material more easily than a broad, blunt surface under the same force. The small tip concentrates the force. Fluids also transmit pressure. In a liquid at rest, pressure generally increases with depth. A deeper point has more fluid above it. The surrounding fluid must support the weight of that material. This is why the pressure underwater becomes greater as depth increases. Atmospheric pressure behaves in a related way. The air above Earth's surface has weight. Near sea level, the atmosphere presses in all directions. Human bodies do not collapse under this pressure because internal pressures and structural forces balance much of it. Pressure also changes when gas temperature and volume change. In a sealed container, heating a gas usually makes its particles move more energetically. Collisions with the walls become more frequent or more forceful. If the volume remains fixed, pressure generally rises. These relationships form part of the ideal gas law. Real gases can deviate from the ideal model, especially under extreme conditions, but the simple picture remains useful. The air around a person may seem calm and empty. Microscopically, it is filled with molecules moving, colliding, rebounding, and transferring momentum. From that restless microscopic motion emerges something that feels completely steady. Pressure is the quiet average of countless tiny impacts. Buoyancy comes from pressure changing with depth. A heavy ship made of steel can float. A small steel ball usually sinks. At first, this can seem contradictory. The explanation begins with pressure. Inside a liquid, pressure generally increases with depth. The lower part of a submerged object therefore experiences slightly greater pressure than the upper part. The forces from the fluid do not cancel perfectly. The result is a net upward force. This upward force is called buoyancy. Archimedes described the relationship more than 2,000 years ago. The buoyant force on an object equals the weight of the fluid displaced by that object. This statement makes floating much easier to understand. Imagine placing a solid block into water. The block pushes some water aside. If the displaced water weighs less than the block, the upward buoyant force is not enough to balance gravity. The block sinks. If the object can displace enough water for the displaced water's weight to equal its own weight, the forces can balance. The object floats. This is why average density matters. Steel is denser than water, but a ship is not a solid block of steel. Its hull contains large spaces filled mostly with air. Taken as a whole, the ship's mass is spread across a large volume. Its average density can therefore be lower than the density of water. The hull sinks only far enough to displace a quantity of water whose weight equals the ship's weight. Add cargo, and the ship settles deeper. Remove cargo, and it rises. The same principle works in other fluids. A helium balloon floats upward in air because it displaces air that weighs more than the balloon and the helium inside it. A hot air balloon uses a related idea. Heating the air inside lowers its density compared with the cooler surrounding atmosphere. The entire balloon system can then experience enough buoyant force to rise. Submarines adjust buoyancy by changing how much water occupies special ballast tanks. Fish use structures such as swim bladders to help regulate their depth. Buoyancy is therefore not a mysterious property of objects. It emerges from fluid pressure and displacement. A floating ship, a drifting balloon, and a motionless fish are all quietly balancing their weight against the fluid surrounding them. Density tells how concentrated matter is. Two objects can have the same size and very different masses. A block of wood and a block of metal may occupy identical volumes, yet lifting them reveals an immediate difference. The metal can be much heavier. Density describes this difference. Density is mass divided by volume. It tells how much mass is contained within a given amount of space. A material with high density contains more mass in the same volume than a material with lower density contains more mass in the same volume than a material with lower density. This simple quantity helps explain many everyday observations. Oil can float on water because many oils have lower densities than water. Ice also floats. This is particularly interesting because solid forms of substances are often denser than their liquid forms. Water behaves differently. When water freezes into ordinary ice, its molecules arrange themselves into an open crystal structure. The same number of molecules occupies more volume. The density decreases. The ice therefore floats in liquid water. This unusual property has enormous importance in nature. Lakes often freeze from the top downward. The floating ice can form an insulating layer while liquid water remains beneath it. Density also changes with temperature. When many materials are heated, they expand. The same mass occupies a slightly larger volume. Their density therefore decreases. Warm air generally becomes less dense than cooler surrounding air. This contributes to convection and atmospheric motion. Density also helps determine whether objects sink or float. An object whose average density is greater than the surrounding fluid tends to sink. One with lower average density tends to rise until forces balance. But density does not tell every story by itself. Shape can change how much fluid an object displaces. Compressibility can matter. Different layers inside planets and stars can have enormous variations in density. At the center of Earth, matter is compressed by the weight of material above it. White dwarf stars contain matter compressed to densities far beyond ordinary terrestrial substances. Neutron stars take this idea much further. Yet the basic definition remains simple. Mass is being compared with volume. Density is not about how large something looks. It is about how closely its mass is packed into space. A feather-sized piece of one material and a smaller piece of another can carry very different amounts of matter. Volume describes the space. Mass describes the amount. Density quietly connects the two. Viscosity measures how strongly a fluid resists flowing. Water pours easily. Honey moves more slowly. Air flows with even less obvious resistance. These differences are related to viscosity. Viscosity describes a fluid's internal resistance to deformation and flow. A highly viscous fluid resists sliding motion between neighboring layers. A low viscosity fluid flows more freely. Imagine liquid moving through a pipe. The layer touching the wall tends to move slowly because of interactions with the surface. Layers farther from the wall can move faster. Viscosity determines how strongly neighboring layers influence one another. Honey has relatively high viscosity. Water has much lower viscosity. This is why honey forms thick, slow streams while water rapidly changes shape. Temperature can strongly affect viscosity. Many liquids become less viscous as they warm. Warm honey pours more easily than cold honey. Gases often behave differently. Their viscosity can increase as temperature rises because faster-moving molecules transport momentum between layers more effectively. Viscosity appears throughout biology. Blood must flow through an enormous network of vessels. Its viscosity influences how easily the cardiovascular system can move it. Mucus uses high viscosity for protective functions. The fluid inside cells has its own complex flow behavior. Viscosity also matters in engineering. Motor oils are chosen partly for how their viscosity changes across temperature ranges. Lubricants reduce unwanted friction between moving surfaces. Pipelines carrying liquids must account for resistance to flow. On geological scales, even materials that seem solid can behave like extremely viscous fluids over very long periods. Earth's mantle is mostly solid rock, yet over millions of years, portions of it deform and flow slowly. This slow movement contributes to plate tectonics and convection within the planet. Viscosity therefore depends partly on the timescale being considered. A substance that seems almost rigid during a few seconds may gradually deform over centuries. Fluids do not all move with the same ease. Their particles exchange momentum in different ways. Some slide past each other freely, others resist. From honey on a spoon to rock moving deep beneath continents, viscosity quietly controls the pace of flow. Flowing fluids can trade pressure for speed. A fluid moving through a changing environment can behave in ways that seem surprising. One useful relationship is associated with Daniel Bernoulli. For certain idealized flows, regions where a fluid moves faster can have lower static pressure than nearby regions where it moves more slowly. This idea forms part of Bernoulli's principle. The full statement is really about energy conservation along a streamline. Pressure energy, kinetic energy, and gravitational potential energy can exchange with one another. Consider fluid moving through a pipe that becomes narrower. If the fluid is approximately incompressible and the flow remains steady, the same volume must pass through each section during the same interval. The fluid therefore moves faster through the narrower region. Under appropriate conditions, the pressure can decrease there. This relationship appears in many systems. A perfume atomizer can use fast-moving air to help draw liquid upward. Carburetors historically used pressure differences created by airflow to mix fuel with air. Venturi meters measure fluid flow by observing pressure changes across narrowing tubes. Airflow around wings is more complicated and should not be reduced to one simple sentence. Aircraft lift depends on pressure distributions around the wing's shape and angle, changes in airflow momentum, circulation, and the surrounding fluid dynamics. Bernoulli's equation can help describe parts of that flow. Newton's laws describe the same physical process from another perspective. The air is deflected. The wing and air exert forces on one another. Pressure varies across the surface. Together, these effects produce lift. The important lesson is broader than any single example. Pressure, speed, and height can exchange energy within a flowing fluid. A parcel of fluid moving downhill may gain speed. A pressure difference can accelerate fluid. A narrowing channel can alter both speed and pressure. Real fluids also contain viscosity and turbulence. Those effects can make the simple ideal equations less accurate, but the underlying energy picture remains powerful. A flowing fluid is not merely matter moving from one place to another. It carries pressure, motion, and gravitational energy together. As the path changes, those forms can quietly trade places. Temperature is not the same thing as heat. The words heat and temperature are often used together. Physics keeps them distinct. Temperature describes the thermal state of a system. At a microscopic level, it is connected with how energy is distributed among the particles and degrees of freedom available within that system. For an ideal gas, temperature is directly related to the average translational kinetic energy of its molecules. Heat is different. Heat is energy transferred because of a temperature difference. An object does not simply contain a certain amount of heat in the same way it contains mass. Energy can be stored internally. Heat describes one way energy moves between systems. Imagine placing a warm metal spoon into cool water. Energy transfers from the warmer spoon to the cooler water. That energy transfer is heat. As the exchange continues, the temperatures move closer together. Eventually, if the system is sufficiently isolated, they approach thermal equilibrium. At equilibrium, there is no net heat flow between them. This distinction explains why temperature alone does not reveal total thermal energy. A cup of boiling water has a higher temperature than a bathtub of warm water, but the bathtub contains much more material. Its total internal energy can therefore be much larger. Different materials also respond differently to added energy. Water has a relatively high specific heat capacity. It takes a substantial amount of energy to raise its temperature. Metals often change temperature more quickly for the same energy input per unit mass. This is why a metal object and nearby water exposed to the same environment can feel different. Temperature measures one aspect of microscopic energy distribution. Heat describes thermal energy in transit. Internal energy describes energy stored among the microscopic motions and interactions within the material. Everyday language blends these ideas. Physics separates them because each describes something different. A warm object may cool, a cold object may warm. Energy passes between them, and once equilibrium arrives, the transfer becomes balanced and quiet again. Heat moves through conduction, convection, and radiation. Thermal energy can travel in several different ways. Three of the most familiar are conduction, convection, and radiation. Conduction occurs through microscopic interactions inside or between materials. Heat a metal rod at one end. Particles in the warmer region contain more thermal energy. Through collisions, vibrations, and electron motion in metals, energy spreads toward cooler regions. The material itself does not need to travel from one end to the other. Energy passes through the structure. Some materials conduct thermal energy easily. Metals are generally good conductors. Materials such as wood, foam, and trapped air are much poorer conductors and can serve as insulation. Convection involves bulk motion of a fluid. Warm a pot of water from below. The lower water gains energy. Its density can decrease slightly. Warmer fluid rises while cooler fluid descends. This circulation transports energy through the water. Atmospheres and oceans use convection on enormous scales. Warm air rises. Cooler air moves. Clouds form. Weather systems develop. Deep inside stars, convection can transport energy through moving plasma. Radiation requires no material medium at all. Any object above absolute zero emits electromagnetic radiation. Warmer objects generally emit more radiation and shift their emission toward shorter wavelengths. Earth receives energy from the sun, largely through electromagnetic radiation traveling across the vacuum of space. Earth also radiates energy back toward space, mainly at infrared wavelengths. A person standing near a warm fire can feel radiant energy even without touching the flames. All three forms can operate at once. A cup of hot tea loses energy by conduction into the cup and table. Convection moves warm air around it. Infrared radiation leaves its surface. Evaporation can carry energy away as well. Thermal systems are rarely governed by just one mechanism. Energy finds several paths. It can pass through matter. It can move with matter. Or it can cross empty space as electromagnetic waves. Across a kitchen, an atmosphere, and the distance between Earth and the Sun, thermal energy keeps traveling through whatever pathway nature allows. Entropy measures how widely energy can be distributed. Entropy is one of the most misunderstood ideas in physics. It is often described simply as disorder. That description can sometimes help, but it is incomplete. A more useful picture is to think about how many microscopic arrangements can produce the same large-scale state. Consider a box filled with gas. The gas contains an enormous number of molecules. Each molecule has a position and velocity. From a human-scale viewpoint, the gas might be described only by its pressure, temperature, and volume. Many different microscopic arrangements can produce those same values. Entropy is connected with the number of microscopic possibilities compatible with the visible state. A system with many possible microscopic arrangements generally has higher entropy. Energy distribution is also important. Imagine a hot object touching a cold one. At first, thermal energy is concentrated more strongly in one place. Over time, energy spreads. The hot object cools. The cold object warms. Eventually, their temperatures approach one another. The final state can be realized through vastly more microscopic arrangements than the initial state. Entropy has increased. This does not mean individual particles are trying to create disorder. They simply follow ordinary physical laws. The statistical result is that states with more possible microscopic arrangements are overwhelmingly more likely. A drop of dye placed in water demonstrates a similar idea. At first, the dye molecules occupy a small region. Later, random molecular motion spreads them throughout the container. There are very many ways for the molecules to be dispersed. There are comparatively few ways for them all to remain concentrated in one tiny region. The dispersed state is therefore far more probable. Entropy also helps explain why some processes seem to have a preferred direction in time. Broken objects do not usually reassemble spontaneously. Warm coffee does not normally absorb random energy from the room and become hotter while everything else cools. Such reversals are not always forbidden by microscopic equations. They are simply extraordinarily improbable for large systems. Entropy turns probability into a direction. Among countless possible microscopic arrangements, nature tends to drift toward the ones that can occur in the greatest number of ways. The second law gives time a statistical direction. Many fundamental equations of physics work surprisingly well in either direction of time. If a video showed two ideal billiard balls colliding, the reversed motion could still obey Newton's laws. At the microscopic level, Many physical interactions have this kind of symmetry. Everyday life seems different. A glass can fall and break. The fragments do not normally leap from the floor and rebuild the glass. Hot tea cools in a room. Cool tea does not usually become hot by drawing thermal energy from slightly cooler surroundings. The second law of thermodynamics explains this asymmetry. For an isolated system, total entropy tends not to decrease. This gives large systems a statistical arrow of time. The past often contains lower entropy arrangements. The future tends toward states in which energy and matter are more widely distributed. Consider two containers. One holds gas. The other is empty. Open a connection between them. The gas spreads through both containers. Nothing in the basic mechanics of individual molecules strictly commands them to occupy more space. They simply move and collide. But there are enormously more arrangements in which molecules occupy both containers than arrangements in which every molecule happens to remain in the original side. The expansion is therefore overwhelmingly likely. A spontaneous return is unimaginably unlikely for a macroscopic number of molecules. The second law does not mean entropy must increase everywhere. Local entropy can decrease. A refrigerator creates a cooler, more ordered thermal state inside its compartment, but it requires energy. It releases heat into the surrounding room. When the entire system is considered, total entropy still increases. Living organisms also maintain complex internal structures. They do so by consuming energy and releasing heat and waste into their environments. Local organization is completely compatible with the second law. The law concerns the total accounting. Entropy, therefore, does not forbid structure. Stars form, crystals grow, snowflakes develop intricate patterns, planets organize into systems. All of these can occur while total entropy increases elsewhere by an even larger amount. The arrow of time is not painted onto each particle. It emerges from enormous numbers of particles and the overwhelming statistics of their possible arrangements. From that quiet imbalance of probability comes the familiar difference between before and after. No heat engine can turn all thermal energy into useful work. Engines transform energy. A steam turbine uses thermal energy to produce rotation. A gasoline engine uses energy released by chemical reactions to move pistons. Power stations convert several forms of energy before electricity reaches homes. Yet no real heat engine can convert every bit of supplied thermal energy into useful mechanical work. Part of the reason comes from the second law of thermodynamics. A heat engine operates between regions at different temperatures. Energy enters from a hotter reservoir. Some becomes useful work. The rest must be transferred toward a cooler reservoir. There is always some rejected heat. One idealized model is the Carnot engine. It does not represent an ordinary machine with literal pistons operating exactly as the model describes. Instead, it provides a theoretical limit on efficiency. Its maximum efficiency depends only on the temperatures of the hot and cold reservoirs, measured on an absolute temperature scale. The greater the temperature difference, the greater the possible efficiency. Even then, perfect conversion is impossible unless the cold reservoir were at absolute zero. That limiting situation cannot be reached by ordinary finite processes. Real engines perform below the Carnot limit because of friction, turbulence, heat leakage, electrical resistance, and many other irreversibilities. This is why waste heat appears almost everywhere. Technology uses energy. A computer becomes warm. A car engine needs cooling. A power plant often releases large amounts of heat into cooling water or the atmosphere. Energy has not been destroyed. It has simply become more dispersed and less available for useful mechanical work. This introduces an important distinction. Energy can be conserved while its usefulness changes. A joule of highly organized mechanical energy can be transformed almost entirely into thermal energy. The same total energy remains. But turning that dispersed thermal energy completely back into organized motion is much more difficult. Efficiency, therefore, has a fundamental limit. Engineering can reduce unnecessary losses. Materials can improve. Machines can become more efficient. But thermodynamics sets boundaries that no clever design can simply ignore. Every engine lives between concentration and spreading. Useful work emerges as energy flows from a more concentrated thermal state toward a more distributed one. Phase changes can absorb energy without changing temperature. Heating usually raises temperature. but not always. Matter can absorb substantial energy while its temperature remains nearly constant. This happens during phase changes. Ice provides a familiar example. Imagine ice at its melting point. Add thermal energy. Instead of immediately becoming warmer, some of that energy changes the arrangement of the water molecules. The solid crystal structure begins to break apart. Ice becomes liquid water. During an ideal melting process at constant pressure, the temperature stays near the melting point until the phase change is complete. The added energy is called latent heat. It changes the phase rather than simply increasing the average molecular kinetic energy associated with temperature. Boiling follows a similar pattern. Liquid water can reach its boiling temperature. Additional energy then helps molecules escape from the liquid phase and form vapor. The temperature can remain approximately constant while boiling continues under steady pressure. A large amount of energy may therefore enter the system without appearing as a temperature increase. The reverse processes release energy. When water vapor condenses into liquid, latent heat is transferred to the surroundings. When liquid water freezes, energy is released as the molecules settle into the solid structure. These exchanges matter far beyond a kitchen. Evaporation from oceans absorbs energy. Water vapor can travel through the atmosphere. When that vapor condenses into cloud droplets, energy is released. This transfer contributes to the behavior of storms and large-scale weather systems. Sweating also uses a phase change. When water evaporates from skin, the escaping molecules carry energy away. This helps cool the body. Different substances have different melting points, boiling points, and latent heats. Pressure also changes phase transition conditions. Water boils at a lower temperature on high mountains because atmospheric pressure is lower. Inside a pressure cooker, higher pressure raises the boiling temperature. A phase is therefore not determined by temperature alone. Pressure and other conditions matter. Matter can change its internal organization, while a thermometer seems almost still. Energy enters, molecules rearrange, and only after the transformation is complete does the temperature continue its climb. Absolute zero is a limit, not a place where everything simply stops. Temperature can become extraordinarily low. Laboratories have cooled atoms to tiny fractions of a degree above absolute zero. Yet absolute zero itself remains a special limit. On the Kelvin scale, absolute zero is exactly 0 Kelvin. This corresponds to minus 273.150 degrees Celsius. It represents the lowest possible thermodynamic temperature. A common explanation says that at absolute zero, all motion stops. Quantum mechanics makes the reality more subtle. Particles cannot generally become perfectly motionless in the classical sense. Quantum systems can retain zero-point energy, even in their lowest possible energy state. The uncertainty principle prevents certain pairs of quantities, such as exact position and exact momentum, from both having perfectly defined values. So absolute zero does not mean every atom becomes a tiny frozen bead with no remaining activity. Instead, the system reaches its lowest thermally accessible energy state. The Kelvin scale is useful because it begins at this physical limit. Temperature ratios become meaningful in ways they are not on Celsius or Fahrenheit scales. 200 Kelvin is genuinely twice 100 Kelvin in thermodynamic temperature. Reaching extremely low temperatures requires removing energy from a system. The colder the system becomes, the harder further cooling generally becomes. The third law of thermodynamics implies that absolute zero cannot be reached through a finite sequence of ordinary thermodynamic operations. Scientists can approach it. They cannot simply arrive there. At ultra-low temperatures, matter can display unusual quantum behavior. Certain atoms can form Bose-Einstein condensates. Large numbers of particles then occupy closely related quantum states. Superfluidity can appear in some systems. Matter may flow with remarkably small resistance under appropriate conditions. These phenomena reveal physics that is usually hidden by ordinary thermal motion. Room temperature matter contains constant microscopic agitation. Cooling reduces that thermal noise. Quantum properties that were once blurred can become easier to observe. Absolute zero, therefore, marks more than extreme cold. It marks a boundary where classical intuition becomes less reliable. Temperature approaches its lower limit. Thermal agitation fades, and the quiet rules of quantum mechanics become increasingly visible. Electric charge comes in two signs. Electricity begins with a property called electric charge. Charge comes in two types: They are called positive and negative. Like charges repel, opposite charges attract. This simple pattern creates an enormous range of phenomena. Ordinary matter contains several charged particles. Protons carry positive electric charge. Electrons carry negative electric charge. Neutrons have no net electric charge. An atom usually contains equal amounts of positive and negative charge. It is therefore electrically neutral overall. But electrons can sometimes be transferred between materials. Rub certain materials together, and a small imbalance can develop. One object gains extra electrons, another loses some. The resulting static charge can make hair rise, attract tiny pieces of paper, or produce a small spark. Charge is conserved. It does not simply appear from nowhere in ordinary processes. If one object gains negative charge because electrons move onto it, something else loses the same amount of negative charge. The total charge remains balanced. Electric charge is also quantized. Ordinary observable charges occur in discrete amounts related to the elementary charge. An electron carries one negative elementary charge. A proton carries an equal amount with positive sign. Quarks carry fractional elementary charges, but they normally remain bound inside particles, such as protons and neutrons. The electric force between charges is described in simple cases by Coulomb's law. The force increases with the magnitude of the charges. It decreases with the square of the distance between them. This resembles Newton's inverse square law for gravity. But electricity differs in one crucial way. Gravity between ordinary masses is attractive. Electric forces can attract or repel. Because positive and negative charges often exist in nearly equal amounts, large-scale objects can be electrically neutral. This is one reason gravity dominates the architecture of planets and galaxies, even though electric interactions between individual particles are far stronger. At smaller scales, electromagnetism becomes central. It helps bind electrons to atoms. It shapes molecules. It produces chemical bonds. It contributes to the forces that prevent solid objects from passing through one another. The simple positive and negative signs, therefore, sit beneath an astonishing amount of ordinary reality. Matter feels solid. Chemistry occurs. Signals travel through nerves and wires. And much of it begins with charge. Electric fields describe how charge influences the space around it. A charged object can affect another charged object without touching it. Physics describes this influence using an electric field. The field assigns a direction and strength to every point in the surrounding space. Place a small positive test charge at one location. The direction it would accelerate defines the field direction there. Around a positive isolated charge, the electric field points outward. Around a negative charge, it points inward. The strength becomes weaker with distance. The field is not merely a drawing made for convenience. It stores energy and participates in physical processes. Modern physics treats fields as fundamental parts of nature. Field lines are often used to visualize electric fields. They are imaginary guidelines rather than physical threads. Closely spaced lines indicate stronger fields. Their direction shows how a positive test charge would tend to move. Two opposite charges create a field pattern connecting the regions around them. Two like charges create patterns that push away from the space between them. Electric fields can combine through superposition. If several charges are present, the total field at a point is the vector sum of the fields created by each charge. This makes complicated arrangements possible from simple pieces. Conductors respond strongly to electric fields because some charges inside them can move relatively freely. In electrostatic equilibrium, mobile charges rearrange until the electric field inside the conducting material becomes zero. Excess charge tends to reside on the surface. Sharp regions can concentrate stronger electric fields. This behavior matters in lightning rods and high-voltage equipment. Electric fields also exist inside electronic devices. They guide electrons through circuits. They control charged particles in sensors and displays. They accelerate particles inside scientific instruments. A voltage difference is closely related to how electric potential changes from one place to another. The language of fields turns invisible influence into something that can be calculated at every location. A charge changes the physical conditions around it. Another charge enters that region and responds. Between them, space is not merely an empty gap. It contains a field quietly carrying the possibility of force. Voltage is a difference in electric potential. Voltage is often described as electrical pressure. That analogy can be useful. But the deeper idea is a difference in electric potential energy per unit charge. A charged particle placed in an electric field may have electric potential energy because of its position. Move it to another position, and that energy can change. Voltage measures how much the electric potential changes between 2 points. The unit is the volt. 1 volt means 1 joule of energy change per coulomb of charge. A battery creates and maintains a potential difference between its terminals. Chemical reactions inside the battery separate charge. One terminal becomes associated with higher electric potential than the other. Connect the terminals through a conducting path, and the electric field established in the circuit can drive charge through the material. Voltage does not itself measure how much charge is moving. That is the role of electric current. Nor does voltage directly tell how difficult the path is for the charge. Resistance describes part of that behavior. This distinction resembles water systems. A difference in height can provide gravitational potential for water. The amount of water flowing depends on the available path. A narrow pipe can restrict the flow. A wide pipe can allow more. The analogy is not perfect, but it helps separate potential difference from flow. Voltage can exist even when no current flows. An unused battery still maintains a potential difference across its terminals. A capacitor can hold a voltage while charges remain separated. When a conducting path becomes available, energy can then be transferred. Electrical systems use many different voltages. Tiny biological signals across cell membranes involve small potential differences. Electronic circuits can operate at a few volts. Power transmission systems use much larger voltages to move electrical energy efficiently over long distances. The number changes. The idea remains the same. Voltage describes an energetic difference between locations. Charge responds to that difference when a suitable path exists. Like water held at different heights, electrical systems can quietly store the possibility of motion before anything begins to flow. Electric current is the motion of charge. When a lamp turns on, charges begin participating in an organized flow through the circuit. This flow is called electric current. Current measures how much electric charge passes through a location during a given amount of time. Its unit is the ampere. 1 ampere corresponds to 1 coulomb of charge passing each second. In metal wires, the mobile charge carriers are usually electrons. This creates an interesting historical detail. Conventional current is defined as flowing in the direction positive charge would move. Electrons carry negative charge. Their average drift therefore occurs in the direction opposite conventional current. Both descriptions are useful. The convention was established before the electron was discovered. Another common confusion concerns the speed of electricity. The individual electrons in a metal usually drift quite slowly. They do not race from a power station to a household appliance at nearly the speed of light. Instead, the electromagnetic influence that establishes the current can propagate through the circuit much faster. A useful analogy is a long tube already filled with small beads. Push one bead into one end. Another can move at the far end almost immediately, even though no single bead travels the whole length during that moment. A wire already contains vast numbers of mobile electrons. When an electric field is established, their collective drift changes throughout the circuit. The electrical energy is carried by the electromagnetic system around and within the conductors, not simply by individual electrons traveling the entire route from source to device. Current can also take different forms. Direct current maintains one overall direction. Batteries commonly supply direct current. Alternating current repeatedly reverses direction. Electrical grids commonly use alternating current because voltages can be transformed efficiently for transmission and distribution. Current also appears outside metal wires. Ions carry electric current in liquids and biological tissue. Electrons and ions carry current through plasmas. Semiconductors use electrons and effective positive charge carriers called holes. The microscopic carriers change. The broad principle remains. Current is organized charge transport. Across copper wires, living cells, and glowing plasma, charge can quietly move through matter. Resistance describes how strongly a material opposes current. Not every conducting path allows charge to move equally easily. A thick copper wire and a thin filament can behave very differently. Electrical resistance describes how strongly a component opposes electric current for a given voltage. For many ordinary components, voltage, current, and resistance are connected by Ohm's law. Voltage equals current multiplied by resistance. If resistance remains constant, increasing the voltage produces more current. Increasing the resistance reduces the current for the same voltage. The unit of resistance is the ohm. Resistance arises from microscopic interactions. In a metal, mobile electrons respond to an electric field, but the material is not perfectly empty. Electrons interact with the vibrating lattice of atoms, impurities, defects, and other features. These interactions limit the organized drift. Energy is transferred from the electrical system into microscopic motion. The material warms. This is called Joule heating. Electric heaters use the effect deliberately. A resistive element transforms electrical energy into thermal energy. Traditional incandescent light bulbs also use resistance. Their thin filaments become hot enough to glow. Resistance depends on geometry. A longer wire generally has more resistance. A thicker wire generally has less. The material itself matters through a property called resistivity. Copper has low resistivity and is widely used for electrical wiring. Other materials resist current much more strongly. Temperature can matter too. For many metals, electrical resistance increases as temperature rises. Semiconductors can behave differently, and some materials enter an extraordinary state called superconductivity at sufficiently low temperatures. Their electrical resistance can fall to zero. Current can then persist without ordinary resistive energy loss. Resistance is therefore not simply an obstacle. It can be useful. Electronic circuits rely on resistors to control currents and voltages. Sensors can use changes in resistance to measure temperature, strain, light, and other quantities. Every conductor permits charge to move according to its microscopic structure. Some offer an easy path. Others make the flow continually share energy with the material around it. Capacitors store energy by separating charge. A capacitor is one of the simplest electrical components. Its basic form contains two conducting surfaces separated by an insulating region. Connect the surfaces to a voltage source. Electrons are moved from one conductor toward the other. One side becomes negatively charged. The other is left with an equal positive charge. The total charge of the full capacitor may still be neutral. What matters is the separation. The separated charges create an electric field between the conductors. Energy becomes stored in that field. Disconnect the voltage source, and an ideal capacitor can retain the separated charge. Connect a suitable path between the two sides, and the capacitor can release its stored energy. Charge flows. The voltage gradually decreases. Capacitance measures how much charge separation occurs for a given voltage. Its unit is the farad. A larger capacitance means more charge can be stored at the same potential difference. Geometry strongly affects capacitance. Large conducting surfaces can increase it. Reducing the separation between the conductors can also increase it. Placing certain insulating materials between them can increase capacitance further. These materials are called dielectrics. Capacitors appear almost everywhere in electronics. They smooth changing voltages, store small bursts of energy, help create timing circuits, separate different parts of signals, assist in power supplies. Camera flashes historically offered a familiar example. Energy from a battery can be stored gradually in a capacitor. Then the capacitor releases that energy rapidly through the flash system. The slow charging and rapid release illustrate the difference between stored energy and power. Capacitors also reveal an important feature of fields. The energy is not best imagined as sitting only on the metal plates. It is associated with the electric field created by the separated charges. A simple pair of conductors can therefore store energy in the space between them. Nothing visible needs to move. Charge waits on separated surfaces. A field remains, and inside that quiet arrangement, electrical energy is ready to flow again. Magnetism comes from moving charge and intrinsic quantum properties. Magnets can seem different from electricity. A permanent magnet attracts certain materials without a battery or visible current. Yet electricity and magnetism are deeply connected. Moving electric charges create magnetic fields. Electric currents therefore produce magnetism. A wire carrying current has a magnetic field curling around it. Wind the wire into a coil, and the fields from different sections combine. The result can resemble the field of a bar magnet. Place iron or another suitable magnetic material inside the coil, and the effect can become much stronger. This creates an electromagnet. Permanent magnets require another layer of explanation. Inside atoms, electrons possess magnetic moments associated with their quantum properties, including spin. Electron motion within atoms also contributes. In many materials, these tiny magnetic effects point in different directions and mostly cancel. In ferromagnetic materials such as iron, interactions can cause groups of atomic magnetic moments to align. These regions are called magnetic domains. In an unmagnetized piece of iron, Domains can point in many different directions. Their effects largely cancel on the scale of the whole object. When many domains become aligned, the material can produce a strong external magnetic field. A permanent magnet therefore contains enormous numbers of microscopic magnetic moments arranged with unusual coordination. Magnetic fields exert forces on moving charges. The direction of the force is perpendicular to both the charge's velocity and the magnetic field. Because of this geometry, magnetic forces can bend particle paths without necessarily changing their speed. Charged particles can spiral around magnetic field lines. Earth's magnetic field influences charged particles arriving from space. Some are guided toward polar regions. Their interactions with the upper atmosphere contribute to auroras. Electric motors use magnetic forces to produce rotation. Speakers use them to move cones and create sound. Magnetic resonance techniques probe matter through magnetic interactions. Electricity and magnetism are not separate worlds. They are two aspects of electromagnetism. Charge at rest creates electric effects. Charge in motion helps reveal magnetic ones. And across both, the electromagnetic field quietly connects matter with the space surrounding it. A changing magnetic field can create an electric field. Electricity can produce magnetism. Magnetism can also produce electricity. This relationship is described by electromagnetic induction. Michael Faraday explored it experimentally in the 19th century. One of the central results is simple. When the magnetic flux through a circuit changes, an electromotive effect is produced that can drive current. Move a magnet toward a coil of wire. The magnetic field passing through the coil changes. A voltage appears. Move the magnet away. The induced voltage reverses direction. Hold everything perfectly still. The changing effect disappears. It is the change in magnetic environment that matters. Generators use this principle. Mechanical motion rotates coils or magnets. The changing magnetic flux produces electrical energy. Power stations may begin with moving steam, flowing water, wind, or other mechanical sources. Generators transform part of that mechanical energy into electrical form. The reverse process appears in motors. Electric current in magnetic fields produces forces and torque. Electrical energy becomes mechanical motion. Generators and motors are therefore closely related devices. Transformers also rely on electromagnetic induction. An alternating current in one coil creates a changing magnetic field. That changing field induces a voltage in another nearby coil. Different numbers of turns in the two coils allow voltages to be increased or decreased. This is extremely important for power grids. Electrical energy can be transmitted at high voltage and relatively low current. Lower current reduces resistive losses in transmission lines. Near homes and businesses, transformers reduce the voltage to more practical values. Induction also explains eddy currents. Changing magnetic fields can produce circulating currents inside conducting materials. Those currents create their own magnetic effects and can generate heat. Induction cooktops use changing magnetic fields to create currents directly in suitable cookware. A moving magnet, a turning generator, and a kitchen stove can therefore share the same physical principle. A changing magnetic field creates an electric response. Energy moves between mechanical and electromagnetic forms, and fields that seem invisible quietly make modern electrical life possible. Light is an electromagnetic wave. For centuries, people debated what light actually was. Was it made of particles? Was it a wave? Classical electromagnetism provided one remarkable answer. Light is an electromagnetic wave. James Clerk Maxwell developed equations describing electricity and magnetism. Those equations showed that changing electric fields can create magnetic fields. Changing magnetic fields can create electric fields. A coupled disturbance can therefore sustain itself and travel through space. When the speed predicted by the equations was calculated, it matched the known speed of light. Electricity, magnetism, and optics suddenly became connected. Visible light is only a small section of the electromagnetic spectrum. Radio waves are electromagnetic waves. Microwaves are too. So are infrared radiation, ultraviolet radiation, X-rays, and gamma rays. They differ mainly in frequency and wavelength. In vacuum, all electromagnetic waves travel at the same speed. This speed is about 299,792 kilometers per second. It is usually represented by the letter C. Unlike sound, light does not need air or another material medium. Electromagnetic waves cross the vacuum between the sun and Earth. They travel through interstellar space. They carry information across billions of light years. An electromagnetic wave contains oscillating electric and magnetic fields. The fields are oriented perpendicular to the direction the wave travels, and in the simple wave picture, perpendicular to one another. The frequency determines many of the wave's interactions with matter. Radio waves can drive currents in antennas. Microwaves interact with materials in ways useful for communications and heating. Infrared is strongly associated with thermal radiation at everyday temperatures. Visible frequencies stimulate photoreceptor cells in human eyes. Ultraviolet radiation can cause chemical changes. X-rays can pass through some soft tissues more easily than through dense bone. Gamma rays are associated with some of the highest energy electromagnetic processes. Yet every region belongs to one continuous spectrum. Nature does not place a sharp physical wall between visible red light and nearby infrared. Human senses simply detect a narrow range. Around that small window lies an enormous invisible spectrum. Radio broadcasts, warmth from nearby objects, sunlight, medical X-rays, and distant cosmic radiation are variations of the same electromagnetic phenomena. Light is not one isolated feature of nature. It is part of a much larger field, gently stretching across the universe. The speed of light is the same for every inertial observer. Speed usually depends on who measures it. A train can move quickly relative to the ground, to a passenger sitting inside. Another passenger may appear completely still. This makes ordinary velocities relative. Light behaves differently. In vacuum, every inertial observer measures light traveling at the same speed. That speed is about 299,792 kilometers per second. It is represented by the letter c. This was one of the foundations of Einstein's special theory of relativity. At first, the statement creates a puzzle. Imagine a spacecraft moving toward a beam of light. With ordinary objects, approaching the source should make the measured relative speed larger, but light does not follow ordinary velocity addition. The spacecraft still measures the beam moving at c. Move away from the light source. The measured speed is still c. Nature preserves the speed of light by allowing measurements of space and time themselves to differ between observers. This is the heart of special relativity. Distances are not completely universal. Time intervals are not completely universal. Different observers moving relative to one another may disagree about both, yet when they calculate the speed of light, they agree. This does not mean light ignores motion. Its frequency and wavelength can change because of relative motion. The Doppler effect still occurs. What remains fixed is its speed in vacuum. The constancy of c also connects space and time. A meter and a second seem like entirely different kinds of measurements. Relativity reveals that they belong to a larger geometric structure. The value of c acts as a conversion factor between spatial and temporal parts of that structure. It also represents a fundamental limit on how rapidly information and causal influences can propagate locally. Objects containing mass can approach the speed of light. Accelerating them closer requires increasing amounts of energy. Reaching c would require unbounded energy in the standard relativistic description. Light itself naturally travels at this limit in vacuum. A constant that first seems like an unusual property of light becomes something deeper. It helps define the relationship between space, time, motion, and causality. Across every empty region of the universe, the same speed quietly ties them together. Moving clocks can tick at different rates. Time feels universal in everyday life. A second on one clock appears identical to a second on another. At ordinary human speeds, this is an excellent approximation. Special relativity reveals a more subtle reality. Observers moving relative to one another can measure different amounts of elapsed time between events. This effect is called time dilation. Imagine a clock moving rapidly past a laboratory. From the laboratory's inertial frame, the moving clock runs more slowly than a clock at rest in that frame. This is not caused by a mechanical defect.